Hello and welcome to Flip Harber for Calculus. In this video we're going to cover section 2.3, calculating limits using the limit laws. Our objectives for this lesson are to be able to apply the limit laws to find limits without tables. Now tables are a way that always work for finding limits, but they're tedious, they're time consuming, they take up a lot of paper real estate. So we're going to try to find ways to solve these limits without using a table. Our outline for this video, we'll talk about the basic limit laws. We'll talk about the most important limit law that you can talk about. We'll take a look at finding some limits from graphs. And then we're going to take a look at some trickery, what I like to call smoke and mirrors. So here is a basic list of some limit laws. Let's go through these. Our top one, the limit as x approaches a of c. What that c means is that it's a constant. So if I ask you, what's the limit as x approaches 2, x approaches 2 of 5? Well, there's no place to plug in that x value. It's just the limit of a constant. That's always just equal to the constant itself. So that's a nice easy one. The limit of a constant is a constant. In the next one, we see the limit as x approaches a of c, a constant, times a function f of x. Now the function f of x has a place to plug in, or plug in. We made this promise a while ago to not plug in. But it has a place for the x, but we've got this constant out front. Well, we can take that constant, since the limit really doesn't do anything with it, we can push that constant all the way outside of the limit, worry about taking the limit of the function, and then just multiply everything, our final answer, by that constant. Our next one, we see the limit of a sum or a difference. If we have the limit as x approaches a of a sum of functions, well, we can go ahead and take those two limits separate, get our answers, and then add up those answers. And the same thing with the difference. We can break these up. Next one down, we see the limit as x approaches a of a product. Again, we can break this up. We can take the limit of each function separately and then multiply after we've taken care of these two smaller, easier functions. Our last one, the limit of a quotient. Again, we can take the limit of each part of this quotient. We can take a limit of the numerator, take a limit of the denominator separately, and then just divide after we have those answers. Now, the most important limit law, because the one that lets us be all sneaky about this and figure things out quickly and easily, is a limit as x approaches a of a function is equal to f of a. So that means that we've just gone ahead and plugged in that a value, even though we made the promise in the last section to not plug in a. If there's no reason we can't plug it in, if we're not getting 0 on the bottom of a fraction, or we're not trying to take a square root of a negative, if f of a exists, well, that's what we say the limit is equal to. So we made this promise when we first learned about limits to never ever just plug in a. Well, right now, we're breaking that promise. We're saying, you know what, there's no reason I can't plug this in. So I'm going to go ahead and I'm just going to plug it in and get on with my life. No tables or anything. So let's take a look at the limit as x approaches 2 of x squared plus 1. This is actually that function that we saw in the previous section. We already used a table. You should have a table in your notes that shows that this limit is equal to 5. Well, we could have figured this out a whole lot easier and a whole lot less work on our paper if we had just plugged it in. There's no reason we can't plug into this simple quadratic. So let's go ahead and just plug in 2. We get 5. That's what our limit was equal to last time. That's what it's equal to now. Now, if we get some sort of mathematical gibberish, now the most common mathematical gibberish that we're going to run into with this stuff is a 0 on the bottom of a fraction, then we're going to have to do a little bit more work. Now let's talk about finding limits from a graph. If they give us some graph for g of x, I'm going to start out with a nice simple quadratic curve. If they give me this cool graph and they ask me what it as x approaches a, I'm just going to read off the y value from this graph and I'm going to report that as my limit. So the limit as x approaches a of some function, I'm just going to read off whatever this y value is from the graph and I'm going to say that's my limit. Now if I've got a more complicated graph, let's muck things up a little bit by breaking this graph like so, and that point is where we want to find this limit. Well, I've got a little bit of a problem. I've got two different y values that I've got to deal with depending on which limit I'm finding. If I find the limit as x approaches a from the left, well, that means that I'm going along this way and I have to report this y value. Let's call that y1. So I would say that this is equal to y1. If I ask what's the limit as x approaches a from the right, so now I'm going along this part of the curve, I have to report this other y value. So I'll say that that is equal to y, so 2, or whatever that y value is that I would read off from the graph. Now this means, if you remember, that if I take the limit as x approaches a, x approaches a, not a approaches a, let's get rid of that. So if I take my limit as x approaches a and you don't see that plus or minus indicating left or right, then what I've got to say is that this limit does not exist because they are approaching different a values based on whether I'm doing it from the left or whether I'm doing it from the right. Okay, now let's talk about some smoke and mirrors. And really there's only one trick that's repeated over and over here. And if I tried to plug this in, and that's really what you should do first and foremost with a limit, just try plugging in the a value. If I try to plug in the a value for this, if I plug in 3 on top, I get 0. Well, that's okay. A limit can approach 0, but I also get 0 on the bottom. That right there is mathematical gibberish. Okay, I can have 0 on the top, I can't have 0 on the bottom. So this is the mathematical gibberish. I can't do this, so I'm going to have to work a little bit harder to get this answer. And what I do is I factor. I do some work at the top, and it turns out that this x minus 3, which should still be an x minus 3 down here, will cancel with this x minus 3 on top. Now I'm trying to take the limit not of x squared plus x minus 12 all over x minus 3. Now I'm trying to take the limit as x approaches 3 of x plus 4. This I can just plug my 3 into and I can get a 7. So by recognizing that this stuff will cancel top and bottom, I went from mathematical gibberish to a limit that I can do, and it's just equal to a 7. Now I can verify this if I actually do a table. If I ask you to do a limit on a test and you're like, I have no clue what to do, make a table. You can always make a table to solve a limit. And if you approach from the left, everything is approaching 7, 6.99, 6.999, 6.999999999. It's getting close to 7. If you approach from the right, 7.01, 7.001, 7.000000001, it's approaching 7. So the table confirms that this limit is equal to 7. Now let's take a look at some more smoke and mirrors. Now I need to recognize that that x squared minus 16 is a perfect square. Now, because I still get my mathematical gibberish, I'll factor the top and bottom. I'll cancel out the x minus 4's. Now I can take this limit, and it's just equal to 8. Okay, here's the smokiest and mirroriest one of them all. I want to take the limit as t approaches 25. If I try to plug it in, which you should always just try to plug it in first, and you can count on one of these on the test, whenever we take the test, you're going to have one that is going to look like you need to do some work, and you could have avoided this work if you had just plugged it in. Just always try plugging them in first. I do get 0 over 0, so now what I need to do is figure out how do I cancel stuff. And the reason this is the smokiest and mirroriest one that we see yet, I'm going to treat that top like a difference of squares. What? There's no square on that t. How do you do that? Well, t can be treated as a square because t is the square root of t squared. Say what? Let me say that again. T is equal to the square root of t squared. I can apply a difference of squares on 25 minus t. It factors into 5 minus the square root of t times 5 plus the square root of t. Do not come to me in class and go, I never would have thought of that. Because you better think of it now. And there's a really big clue that I want to do this because in the bottom I have 5 minus the square root of t. That can cancel. When that cancels, I can go ahead and just plug in 25. The square root of 25 is 5. 5 plus 5 is 10. Now, I can't show you all the tricks, okay? All the limits that you're going to see in this section will work out, though. You've got to have a little bit of faith on that. Try to look past the distraction. Work on the tops of the fractions. Try to factor them out somehow. If you see little fractions, try to get common denominators so that you can get rid of those little fractions. Okay? It's time for you to go to work. I'm done talking, so I'll see you in class and I'll see you online.